Hello everyone, welcome to the first tutorial session on the NPTEL course of AE20, which is the introduction to CFD. So let me just share my screen now. So today we will be going through the tutorials on week 0, which is the introduction to numerical methods and basic solution methodologies which exist in CFD. My name is Sumant Marav. I am a PhD research scholar in Department of Mechanical Engineering at IIT Bombay. So let us see the first question. So the first question is mainly based on finding the roots of equation, a nonlinear equation using Newton-Raphson iterative scheme. So the function is given as x cube minus 3x square plus 1 is equal to 0. And so basically they have asked what is the formula for finding the roots of the equation. So mainly if we see the Newton-Raphson method, which is one of the iterative scheme to find the root of a nonlinear equation, then we get the solution as x at the n plus 1th iteration is equal to x at the nth iteration minus the function divided by its derivative at the nth iteration. Okay, so this is in the practicality, we assume initial value which is denoted by x0, and then we iteratively try to get the values of x till they converge. So that is how it is usually done, but here they have just asked us to find the value of xn plus 1, which is pretty much straightforward. So f of x anyway is given. It will be x cube n minus 3x square n plus 1. So n basically means nth iteration. And then if we take the derivative f dash of x of xn, it will become 3xn square minus 6n. Okay, fine. So then the second part is to substitute this f dash and f in this particular equation. So you end up with xn plus 1 equal to xn minus the function and divided by its denominator. So if you further simplify it, you will end up with this particular equation, that is the most simplified form. So if you try to compare it with the options which are given here, you can directly find out that this answer is close to or same as the option number A. Okay, so the correct answer is option number A. Fine. So let us see the second question. So basically it is based on the matrix system. So it is given that if the determinant of a matrix goes to 0, then which of the following statements are correct? Now if we see a matrix whose determinant is 0, basically the way in which we calculate A inverse is as follows. So you all might be knowing it very well from your from your 11th 12th studies itself. So 1 divided by determinant of A into adjoint of A, that is the transpose of cofactor of A. So now it's given that determinant of A is 0. So you can directly understand that A inverse does not exist. Since A determinant of A is 0, you cannot find the A inverse. So that is the one thing. So then definitely option number C is correct. Also, if A inverse does not exist, it indirectly means that A is a singular matrix. Remember, the definition of singular matrix is that it's a matrix which cannot be inverted. So such matrix are called a singular matrix. So obviously B is also correct. So B and C are correct. So if you come to the last option, A is an identity matrix. So if you consider an identity matrix, say 2 by 2, then the determinant becomes 1. In fact, for any order identity matrix, determinant is always equal to 1 and it is not equal to 0. So option D is incorrect. So only B and C are the correct answers here. So this is the second question. Now coming to the third question, again it is based on the matrix system. Now indirectly they have given that this matrix which is given, it's a singular matrix. So if we remember what happened in the second question, so the determinant was 0 for a singular matrix, right? So we will apply the same concept here. Basically we have to find out the x, okay? We have to find the value of x here. So basically we'll apply the same concept that determinant should be equal to 0 so that it becomes non-invertible, okay, to become singular matrix. So that is why determinant of B is equal to 0. Now you just simplify this and you will end up with the value of x, okay. So the value of x goes to 21. If you just simplify this, you will easily get the answer, okay. So the week 0 is basically on fundamentals of the numerical methods and mathematics. So it's very preliminary exercises. Now if you see the fourth question, it is a little bit related to the fluid mechanics side, okay, I would say. Basically the velocity field has been given, it's a vector field and it's a three-dimensional field. So what they have asked is to find the local and convective acceleration along the z direction, okay, and the coordinates at which we have to find these accelerations are also given. Now in fluid mechanics, the basic fluid mechanics course, we have already learned about the local and the convective acceleration, okay. So the total acceleration, it is denoted by capital dv by dt, which is called as material derivative. Now this material derivative in fact is decomposed into two parts. One is the local acceleration component, the other is the convective acceleration component. So what happens is that basically if you take the momentum equation, so basically the rate of change of momentum is attributed to two facts. So one is the uh, change in momentum which is happening inside a control volume. If we say finite volume method, then we come across control volume. So momentum which is changing inside a control volume, momentum increase inside a control volume, which is happening from within the control volume. So that is the local part. Now there is another part also, like there is a change in the momentum due to the flux, incoming flux and the outgoing flux of momentum across the surface of the control volume. So that is usually called as convective acceleration. That is basically it happens because of motion of molecules, I would say. Because of that, this convective part comes into picture. So you might have already learned these things anyway in basic fluid mechanics course. So I was just revising that, and you have also learned the momentum conservation equation, which we will be using in CFD. So that is why you need to kind of know these things. That is why this question has come in. Now, if you see, the local acceleration is the partial derivative of the vector field v with respect to time. Okay, and it turns out that it becomes just 37 k cap. Now, anyway, in the question, it has been asked in the z direction. Okay, so directly it is 37 because the local acceleration is present only along the z direction only, and the magnitude is 37. So 37 will come local component. Two options are there here. We have to also find the convective acceleration. The convective acceleration, you already know how it is calculated. Just remember the momentum equation wherein you had the material derivative of velocity. Okay. Sorry, I have not put an arrow here. Where it's the partial derivative of the v vector with respect to x. Okay. and then similarly the y component of velocity and the partial derivative with respect to y, and then the partial derivative with respect to z. Now Vx you already know, that is x component 15xy square, that I have substituted here. Okay, then partial derivative of the vector with respect to x you have to calculate. Okay, so if you kind of calculate this, okay, you kind of get terms which involve I cap, j cap, and k cap, all the three terms. But you want the answer only along the z direction. So I have just clubbed the terms which come in z direction, that is k cap. So only k cap terms I have considered here. Okay. If you see this 15xy square and 22xy will come in, and then if you see the second term, then it is 40y square z, 11x square. Okay, so 40y square z, 11x square. Now these are the components along the k cap, that is the z direction. Okay, so if you substitute the coordinates 1 1 1, you finally end up with minus 770. So 37 comma minus 770, which corresponds to option number C, should be the correct answer. Yeah, so this is the answer for this question. Now, if we come again to the fifth question, it is again the basic fluid mechanics. Just for revision purpose, it has been given here. So, you know already what is the equation which needs to be satisfied for the mass conservation. Okay, so they have given the vector field for velocity. Okay, vector field is already given. You have to check, verify whether it satisfies the mass conservation or not. That's very easy, you can do it, I think. So, and the second part is, if so, then determine the expression for stream function. Okay, so first let us see whether it satisfies the mass conservation or not. So what is mass conservation? The net rate of mass entering the control volume minus leaving the control volume should be equal to the mass change which is happening in the control volume. So there should be no net rate of increase or decrease of mass. That is, mass cannot be generated. Okay, so that is the main concept here. At least for the, I would say, for the incompressible uh, fluids. So if you see, that is, the equation is dux by dx plus dy by dy, that should be equal to 0. Let us see what happens. So if you see, dux is minus 7y square, duy is minus 9x. So anyway they are 0. So yeah, mass conservation is satisfied. So option D is not valid. Okay. Then the second part is to calculate the stream function. Okay, so basically this stream function kind of gives the direction in which, if you draw perpendicular at any point of the streamlines, so basically you get the direction of motion of the fluid. Okay, so that is what is mainly meant by the stream function. That is the practical, I would say, practical value. I mean, what would you say, the practical application of stream function? Yeah, application would be a better word. So it is directly calculated by using this formulation, integral of ux dy minus uy dx. It basically comes from the mass conservation itself. Okay. So if you just substitute again these values and the integral, okay, it comes out to be minus 7y cube plus 9x square. Okay, plus some constant value. Here they have not given the constants. Okay, let us ignore that. Okay, minus 7y cube by 3 and plus 9x square by 2. I think it should be option number B. So the correct answer is option number B. So the sixth question, let us see. Again, it is based on the fluid mechanics concept. Okay, so the x component of velocity in a 2D incompressible viscous flow over a flat plate is given by, okay, so assume that there is a flat plate and above that flow is happening, I mean fluid is flowing. So the velocity field is given along the x direction, yeah, the x component, okay. So in this there is a y term, okay. So the distance y is measured from the plate surface along the normal direction, okay. So basically from the plate surface, if you measure in the normal direction, whatever distance you get, that is y. Now check whether the flow is irrotational, and if it is not, then find the expression for angular velocity. Now how do you check whether the flow is irrotational or not? Just take the curl of the velocity. If it comes out to be 0, then basically there is no rotation component involved in the flow. So we are assuming that the V and W component, that is the Y and Z component, are 0. Okay. So with that in mind, let us calculate the curl of the velocity. The curl of the velocity is turning out to be some value. It is not equal to 0. Hence, the flow is not irrotational. Okay. Okay. It is rotational. I mean there is some angular velocity. Okay. So if you just work out this, you will directly get out. You know how to calculate the curl of velocity, I guess. So you just take the determinant of the matrix, wherein along the first row you have the direction I cap, j cap, k cap. Second row you have, I mean, the partial derivatives. I mean, if you kind of expand this and then write also, finally you will get this particular form only. I have just directly written this, I mean, the determinant form, okay. And then you have u, v, and w. Anyway, v is 0, w is 0. Okay, you end up with mainly, I guess, du by dz and du by dy. So you have only k component because du by dz is anyway 0. Du by dy you have, so only k component comes in. Sorry, the k cap is missing here. Okay, so along the z direction you have some rotation. Okay, so the second part is, if not, then calculate the angular velocity. Yeah, that is pretty easy. You just have the expression that angular velocity is nothing but the rotation, half of the rotation. Okay, so you end up with minus 3 by 8 plus 3 by 4 into y square, which is option number C. Yeah. So let us see the last question. This is based on, I guess, fluid mechanics. Yeah, again fluid mechanics. A pitted static tube is placed inside a duct through which air is flowing at a constant speed. Okay, you have a duct in which air is flowing at a constant speed. It is flowing. Okay. Then you have the stagnation and static pressure ports of the pitted static tube are connected to two limbs of a U-tube motor manometer. So basically, they are trying to measure the velocity, I guess. So they have connected the pitted static tube at 2 points in the duct, at wherein there is some pressure difference, and we know that pressure difference also because delta H is given. Delta H recorded in the manometer is 60 mm. So what happens is that that the second point, which they are telling us stagnation, the velocity becomes 0. Okay, because of the pitted tube, it becomes 0. So one velocity we know that it is already 0. So at the upstream point of the flow, basically they are asking calculate the air speed inside the duct. The upstream point, what is the velocity? So you have the Bernoulli equation here, the conservation equation, the total kinetic energy plus the pressure energy remains constant. So you already know that. We are ignoring the difference in the height because it's a straight duct. Okay, assuming that it is a straight duct, so there is no potential component. Okay, so that is being ignored in this equation. So you have only p plus half of rho v square is equal to constant. So now you already know that V2 is 0 because it's the stagnation at which the P2 is measured, the pressure is measured. Okay. So that is why V2 goes to 0. Now you have P2 minus P1, which is being measured by a YouTube water manometer, okay, and delta H is given as 60 mm. So rho of water G into delta H, that is nothing but the P2 minus P1. It is measuring the pressure difference. It is rho W G into delta H. Okay, so you can directly then find the V1 value as given in this particular expression, which is nothing but the square root of 2g into delta h into the rho w by rho a. Okay, you can directly find it out, I hope. So that comes out as 31.3 meter per second. If we see the option, I think it's in the option number B. Okay, so these were some of the questions. Mainly we started with some mathematics based on linear algebra, the matrix systems, and then the solution to the nonlinear equation using Newton-Raphson method. That was the second thing, and then slowly we entered into the fluid mechanics part, wherein we saw some basic fluid mechanics questions, how we can try to solve them. These are just prerequisites for the CFD course. You will be applying this and then in a computational setup. Okay, so that is the main objective. Okay, yeah, so thank you for listening. So if you have any doubts, you can contact me on my mail id, which is given here. Okay, so thank you. If you have any doubts, maybe you can ask, or else we can just close this meeting.